Good morning, everyone. Today, we'll be presenting the Chapter 5 of Fundamentals of Electronic Communication, focusing on the fundamentals of frequency modulation. We'll explore the basic principles and application of this crucial modulation technique.
Have you ever wondered how radio stations broadcast music and talk shows without interfering with each other? The answer lies in modulation techniques. And today, we'll be focusing on one of the most important, the frequency modulation. This presentation will cover the fundamental principles and show you some real-world applications of FM. Now, we're diving into the world of radio waves and exploring a crucial concept, the frequency modulation or FM. You've likely heard the terms AM and FM radio, but what exactly differentiates them? Let's find out. FM is a type of modulation which essentially means it's a way of encoding information onto a radio wave. In FM, the K is the frequency of the carrier wave. Notice that the amplitude or strength of the carrier wave stays constant. Instead, it's the frequency that changes. This change in frequency directly reflects the amplitude of the audio signal we're transmitting. A louder sound corresponds to a higher frequency shift, and a softer sound corresponds to a smaller frequency shift. This diagram helps visualize the concept. See how the carrier wave's frequency increases and decreases in response to the audio signal? The amplitude of the carrier wave itself remains unchanged. This is the core difference between FM and AM, where the amplitude of the carrier wave varies instead of the frequency. Because the information is encoded in the frequency, not the amplitude, FM is far less susceptible to noise and interference. Think about static on the radio. That's noise affecting the amplitude of the signal. Since FM ignores amplitude changes, it's much clearer and less prone to distortion. This is the major advantage leading to higher quality audio broadcast. Let's delve into the K parameters that define a frequency modulation signal. Understanding these parameters is crucial for comprehending how FM works and its characteristics. First, we have the carrier frequency. This is simply the frequency of the unmodulated carrier signal, or the base frequency of the radio wave before any information is added. Think of it as the foundation upon which our radio signal will be superimposed. Next is the modulating frequency. This represents the frequency of the audio signal we want to transmit, the sound itself. It's the information we're encoding into the carrier wave. The frequency deviation is the maximum change in the carrier frequency caused by the audio signal. This is directly proportional to the amplitude of the audio signal. A louder sound leads to a greater frequency shift. Finally, the modulation index. This is the ratio of the frequency deviation to the modulating frequency. The modulation index is critical because it determines the bandwidth of the FM signal, the range of frequencies the signal occupies. A higher modulation index means a wider bandwidth, generally allowing for better radio quality but requiring more transmission space. To recap, we've covered 4 essential FM parameters: carrier frequency, modulating frequency, frequency deviation, and the modulation index. Understanding these parameters provides a solid foundation for grasping the principles of frequency modulation and its application in radio broadcasting and other communication systems. Next, we will introduce the concept of an FM waveform. An FM waveform or frequency modulated waveform is a signal where the frequency of the carrier wave is changed to represent the information being transmitted. Notice the K here is frequency, unlike amplitude modulation, where the amplitude of the wave changes to represent the signal. In FM, it's the frequency that varies. The light bulbs serve as a simple analogy. Imagine the brightness of the light bulb representing the amplitude of the audio signal. In FM, the brightness serves as the amplitude, stays relatively constant. However, the frequency of the lights flickering would change to represent the information. A brighter light or a louder sound might correspond to a faster flickering rate or higher frequency, while a dimmer light or softer sound could correspond to a slower flickering rate or lower frequency. This change in frequency is what carries the audio information. The receiver then decodes this frequency changes back into the original audio signal. This is why FM radio generally offers better sound quality than AM, as it's less susceptible to noise that affects the amplitude of the signal. In essence, an FM waveform uses frequency variations in the carrier wave to transmit information, maintaining a constant amplitude for better noise immunity and audio quality. Next, we will illustrate the FM spectrum. The FM spectrum is the range of frequencies occupied by a frequency-modulated signal. This includes the carrier frequency itself, but also numerous sidebands. These sidebands are created during the modulation process, where the frequency of the carrier wave varies to represent the audio signal. The presence of these sidebands is what results in a wider bandwidth for FM compared to AM. The rainbow is a visual metaphor for the FM spectrum. Each color represents the different frequency component within the overall FM signal. Just as a rainbow is composed of many colors spread across a range of wavelengths, the FM spectrum is composed of many frequencies spread across a range of frequencies. The main arc of the rainbow represents the carrier frequency, and the broader spectrum of colors represent the sidebands. The wider the spectrum, the more information can be transmitted, leading to higher fidelity audio. This wider bandwidth is a key reason why FM radio generally offers better radio quality than AM. The broader range of frequencies allows for a richer, more detailed sound. However, this wider bandwidth also means that FM signals require more radio frequency space than AM signals. In short, the FM spectrum encompasses a broader range of frequencies than AM, including the carrier frequency and numerous sidebands generated by the modulation process. This wider bandwidth is directly related to the higher fidelity audio capabilities of FM.
Why use FM? FM offers several advantages that make it superior to other modulation techniques, such as amplitude modulation. First, better signal-to-noise ratio, or SNR compared EM. FM signals have a higher SNR compared to EM, resulting in clearer reception. Second, wider bandwidth allows for more information to be transmitted. The increased bandwidth of FM enables it to carry more detailed and richer audio signals, enhancing listener experience. Third, high-fidelity audio reproduction. FM provides excellent sound quality, make it ideal for music and voice transmission. And lastly, less susceptible to noise and interference. Since FM encodes information in frequency changes, it is less affected by electrical noise, which mainly impacts amplitude.
While FM has many strengths, it also has some drawbacks. First, requires a wider bandwidth than EM. FM needs significantly more spectrum space, which can limit its availability in crowded frequency ranges. Second, more complex circuitry than EM. FM system required more complex and costly equipment compared to EM system. The design of FM transmitter and receiver involves advanced technology, making them harder to build and more expensive. And lastly, can be affected by multipath propagation. Multipath propagation happens when a signal bounces off objects like buildings or the ground before reaching its destination. These reflections can be mixed with the main signal, causing interference or distortion, especially in cities or areas with lots of obstacles. Applications of FM. FM is used in many applications because it provides clear and reliable signal transmission. First, radio broadcasting. FM is used by radio stations to deliver high-quality sound for music and talk shows. Second, television broadcasting. Some TV channels use FM to send audio signals clearly. Third, satellite communication. FM helps send strong and reliable signals over long distances in space. Fourth, wireless microphones. FM ensures stable and interference-free sound for events and performances. And lastly, two-way radios. Police, military, and emergency teams use FM for dependable communication in critical situations. FM is chosen for these uses because it resists noise and delivers better sound or signal quality. Conclusion: frequency modulation, or FM, varies and carries waves frequency to transmit information, offering high fidelity audio and noise immunity but requiring wider bandwidth and more complex circuitry than EM. Its applications span radio, television, and other communication systems. However, FM has limitations such as the need for more bandwidth and complexity in equipment. By understanding these fundamentals, we can appreciate why FM remains a cornerstone or modern communication technologies.